joining this session. It's lovely to have each one of you here. And thank you so much for telling us where you're joining from. I can see you all have joined from different places here. And I'm going to jump into today's session, which is Eco-Innovators, the Science of Saving the Planet. We are honored to have here with us Dr. Zhu Yunzhen. She is a rockstar researcher and a junior associate professor at the Faculty of Bioenvironmental Sciences at Kyoto University of Advanced Science. So what I have seen, she's really had some exciting ideas, one of which is actually using sunlight to turn waste into clean energy. So yeah, with such kind of great ideology, she's going to tell you all about how science can make a real difference in saving our planet. Along with Dr. Zhu, we have Mr. Kiyoshi Takeda. He's the Director of International Admissions Office at POS. And Mr. Kandar Dhingra, who's the Assistant Recruitment Advisor at POS. So we're very happy to have each one of you here. They'll be here to share more about Japan experience, and they'll be happy to help you with any of the questions that you might have had during or after the session. I have a small request from each one of you. Please put your questions in the Q&A box so that we can help you with it. And without any further ado, Dr. Zhu, please take the session ahead.
Okay, thank you. Thank you for introduction. So now I will share the screen. The presentation. And okay, can you see the screen?
Coming up, yes.
Slide. Okay, thank you so much. And welcome to all the brilliant students and guests. And my name is Zhu Yunxin. In Japanese pronunciation is Xu Yinking. And it's my great honor to to show my research and my feelings, my experience with all of you. So today we are going to explore the power of bioenvironmental sciences, particularly the power of the chemistry and biology on solving the planet problems, the waste. And by the end of the day, I hope to show you that you are not just learn the chemistry and biology as a subject in your textbooks. They are actually cutting-edge weapons we can use to tackle some of the biggest environmental challenges. So let's get started. So before we deep, please let me give you a quick roadmap of our set the stage, understand why I will introduce to one of the nature's most brilliant technology, the anaerobic digestion, combining the power of biology and chemistry and its magic effect on converting the organic waste into the valuable resources. And then in part 2, we will zoom into the sciences what I made. And this is where I share my team's research on the innovative approach for waste to energy conversion. We will explore the key challenges in this processes, the ammonia inhibition, and how we are tackling it with a surprising tool, the solar light. And in part 3, we will look ahead to your future. We will explore the career map for young professionals. You will know that getting a degree in biosciences isn't just about working in a lab. It opens the doors to vast universe of academic and industrial opportunities. I want to show you that the incredible path you can take to make a difference. So that's our plan from the big picture to the sciences in the lab and to your future career. So I believe at the end of you listening today are the ones who will take those of the idea and illuminate your own future. So before I start, please allow me to introduce myself. I come from a beautiful city of Qingdao in Shandong, China. Since last year, I've started to work as a junior associate professor in the Faculty of Bioenvironmental Sciences at Kyoto University of Advanced Sciences in Japan. And my research focused on some exciting areas such as the environmental purification, finding ways to turn the biomass like biowaste into the useful energy, and developing a better solution for sustainable waste management. I also dive deep into the applied biochemistry and bioprocess engineering, which can help us tackle the pollutions and the energy issue. And throughout my career, I have been lucky enough to publish my findings in multiple international journals in the past 4 years. So, my academic journey in the bioenvironmental sciences started from much like yours, with a deep curiosity about how the biology and the chemistry can solve the real world problems. And my academic path began in China, where I earned my bachelor degree in food sciences and engineering from Shandong Agricultural University. This is where I built my foundational knowledge in biological process and chemical principles, a crucial combination for the work I do now. And driven by a passion for the green food system and environmental solutions, I moved to Japan to pursue the deeper research. At the University of Tsukuba in the Graduate School of Life and Environmental Sciences, I dedicated the next 6 years to my master's and doctoral studies. And during these years, I truly delved into the fascinating world of microbial ecosystem and waste valorization and published a research paper and exchange ideas with the international researchers during the conference and similar like today. All of this laid a solid groundwork for the talk we're having today. And after I got my PhD, I continued at the University of Tsukuba as the postdoctoral researcher. And in this role, I was able to deepen my research and began to learn my own project focused on optimizing the biological system for energy and the resource recovery. So now, just recently, I opened an exciting new chapter in my career. I'm now a junior associate professor, as mentioned before, and I lead my own research group in the bioprocessing technology lab, where our mission is to develop an innovative biotechnology to convert waste or garbage into the valuable resources. So, from students to researchers and to freshmen in faculty, my entire career has been fueled by the belief that biotechnology holds the keys to more sustainable planet. I'm not just here to talk about a serious, uh, I'm here to share the practical, the experience, and the exact work happening in labs right now, and to show you how you can be a part of this story in the future. So let's start with the part one. And to begin our journey, we need to first understand the scale of the challenge we're facing now, the waste, a global challenges. Let's start with the food waste. Globally, we throw away 1.3 billion tons of food every year, and according to the United Nations State report, this is enough food to feed 3 billion people. And this means that the wasted food is enough to fulfill almost one-third of entire world population going hungry. Next, please consider the agricultural residues. The leftover stalks, husks, and straw from the farming, billions tons of this biomass are generated and burned in the field and lead to the toxic smog, massive air pollution, and carbon emissions. And finally, there is the wastewater. A report states that 80% of the world wastewater is returned to our environment, to our rivers, lakes, and oceans without any treatment. This means that it's laden with the chemical, nutrients, and the pathogens, polluting our precious freshwater resources and harming the aquatic life. Look at this news. When I first saw it, I was really shocked by its incredible scale. This is the Gaspur landfill, a massive old waste dumping site in India. It's established in 1984 and it has grown in a towering garbage mountain over 70 meters. So it has earned a nickname, the Mountain Everest of Trash. And this mountain isn't just sitting still, it's actually growing so fast and getting so tall that authorities had to consider to install aircraft warning light on the top of it to prevent the airplane from crashing into it. Think about that for a second. We have treated our own garbage like a dangerous mountain peak. This is not science fiction. This is current state of waste challenges happen all around us. We are facing a mountain waste management crisis that threatens not only the environment but also the public and health and the economic stability. As one of the most popular countries in the world, India generates approximately 62 million tons of waste annually, of which only 75 to 80% is collected, and less than 30% is treated or recycled. And a huge part of that waste is organic, including the food scraps from our kitchens, agriculture leftover from our farmers, and animal manure. And this organic waste is the major contributor in climate changes at its release methane, a greenhouse gas that is over 25 times more harmful than carbon dioxide as trapping heat in our atmosphere. This is not just happened in India, it happened all around the world. As mentioned before, the FAO, the Food Agriculture Organization, and reported that every year, about 1.3 billion tons of food, or one-third of the world food production, is wasted, which is quite issues in our global food system. While when we focus on Japan, as reported, every year we discuss 5.2 million tons of food waste. This is equal to 1,400 large trunks with a 10 tons capacity being filled with food waste every day. And when counting this amount based on each person, every Japanese citizen wastes a bowl of rice daily. This is not only because of over preparation or expired food for a household, but also due to the supermarket and restaurant discard extensive unsold items. And this generated waste doesn't just disappear. It further contributes to the greenhouse gas emissions and resources inefficiency. So how it affected the environment? Look, if we not treated the waste and directly dispose it into the environment, we call this method as landfills. As we've seen the large landfill site in India before, it takes a long time to completely degrade the organics, and during this process, large amount of methane emit. Methane, remember, is much more harmful to the environment compared to the carbon dioxide. And this method is commonly used in the developing areas, while in the developed countries, such as Japan, most of organic waste is incinerated or burned at high temperature. As we all know, this process not only costs energy, but also releases a significant amount of carbon dioxide into the atmosphere and leading to the environmental burdens. According reported by the World Wildlife Fund, the WWF, food waste contributes roughly 10% of global carbon dioxide emission annually, and this is a double amount of carbon dioxide emitted from cars in the US and Europe over a year. Our cities are generating waste faster than we can manage it, and our traditional method, like open dumping and burning, are causing severe environmental and healthy problems. But what if I told you that this mountain of waste isn't just a problem? What if I told you that the tremendous opportunity lies behind this for building a sustainable society? an opportunity that we can harness the power of the biology and chemistry to manage the waste and cure the diseases of our environment. Let's think of chemistry as our master detective. It gives us the tools to investigate its substance at the molecular level, help us understand what its pollutant is made of, and how we can break its chemical bonds apart and transform it into the smaller, simpler, and harmless compounds. While for the other partners, the biology is our incredible cleaner crew. For billions of years, our nature mother has developed the world's most incredible recycling process with the help of microbial armies, including the bacteria and archaea, that specialize in breaking down the complex material into harmless byproducts. They are the nature tiny and powerful factories. And when we bring them together, we create something more powerful, the biotechnology. This is where we start to engineer the natural process instead of only observing it. We take these natural phenomena and optimize them to serve human needs. And one of the most brilliant natural biotechnology is a process called anaerobic digestion. It sounds complicated, but I'm sure that you are already familiar with it. Have you ever wondered how a core digests its grows? Inside its stomachs, an environment without any oxygen, a community of microbes work together to break down the tough plant materials such as cellulose, eating the organic carbons it contains and converted them into the biogas, such as hydrogen and methane, and which is a form of clean energy. This is exactly the same process that not only happened in the core stomachs, but also in the wetland as well as the bottom of the landfills. And that's why it causes methane emissions. But here's the key: we can reduce the methane emission. We can mimic this natural process in the biological digest system and build our own mechanical stomachs called the biogas or a biogas digester or biogas plants. We put the organic waste, such as kitchen scraps or farm waste, into the sealed tank. And in the same way, we let those bacteria and archaea go to work. After sometimes like 3 or 4 days later, the output is two incredible useful things. Firstly, the biogas, which most composed of methane. Instead of directly emitted to the air, now we capture it and use as a clean fuel for cooking, electricity, or even running a car. Secondly, the nutrient research salary will be obtained, called digestate. This is a fantastic organic fertilizer that can go back to nourish our soils. This is how the anaerobic digestion works for waste management, a positive loop for recycling the carbon source. What's more behind this process is through the anaerobic digestion process, every kilogram of waste could be transformed into enough biogas of 200 liters to power a stove for at least 1 hour, and compared to just throwing it in the landfill. This process can reduce the greenhouse gases emission by up to 80%. So this is not just a theory, it's a win-win solution that uh, manage the waste, create renewable energy, fight climate changes, and produce fertilizer. For, for one thing, it reduces the landfill volume and prevents the pollution, the health hazards, and risks to local residents. For another thing, it provides the renewable biogas, reducing the resilience on the fossil fuels. Most importantly is that it happened in a completely sealed and closed system where we can capture the methane instead of directly emission. Not mention the created digested as a fertilizer could in return benefit the food system by improving the soil health and reducing the chemical use. Now we've just seen how amazing anaerobic digestion is, but why it has not been widely applied and solved all the problems mentioned above. Well, the point is, the natural process, although brilliant, it happened quietly slow. It can take weeks or even months for those microbes to finish the job. So generally, the practical application of anaerobic digestion system with a positive profit is not easy. So in this slide, I'm showing three reasons that may influence the efficiency of anaerobic digestion process. Now, I want all of you to act as researchers, use your intelligence and the scientific intuitions to think about and choose which is the biggest challenges for the anaerobic digestion process. And please participate us either by scanning the code or join us via the access shows at here. And to choose what do you think is the biggest challenges in the anaerobic digestion? Whether it's due to the organic byproduct accumulation or due to the presence of the inhibitory substance or due to the lazy bacteria. And I think the time is so limited, so later we will check the result. So now I will give you a brief introduction of those challenges that happen in the anaerobic digestions. So when the bacteria in the anaerobic system meet the inhibitory substance such as ammonia, which we will learn in the following section, the microbial activity will be firstly affected and followed by the community structure and the function will be shifted. So that microbes are unable to eat and digest all of the organics. And finally leads to the accumulation of fermentative byproducts such as organic acid. And as we all know that acidic condition is not suitable for all the livings. Therefore, more and more microbes cannot resist the pressure and stop to work, and this intensifies the inhibitory effect again. So finally, the continued accumulation and inhibition lead to the negative loop, resulting the low efficiency or even the failure of the anaerobic digestion system. So after listening this kind of introduction, I think you all have some answers in your mind. Indeed, all of these three challenges is the biggest challenges happened in the AD system and influence the efficiency of the whole process. Yeah, I think this kind of negative loop sounds quietly complicated, but this is exactly what makes this technology so fascinating and where my research comes in. From this part, I will share my research on developing a novel strategy and to solving the about problems and advancing the AD system just by simply utilizing the power of solar light. So before we get deeply, I will briefly introduce the main content of the recent research. So as mentioned before, the anaerobic digestion is an attractive approach to realize a sustainable conversion of waste into the renewable energy. However, the process efficiency usually limited by the higher ammonia level and causing the inhibition of microbes activity and community structure, leading to the repressed bioactivity, low methane yield, or even the failure of the digester. And to solve these problems, my group innovatively developed a light stimulation strategy by simply exposure to light. The microbial activity was stimulated and their functions and cooperations was recovered for better vaccine production. And in recently published studies, we focus on further advancing this process for future use from following aspects. Firstly, by optimizing the light parameters such as light intensity, illumination time, and the wavelength to maximize the performance of the developed reactor. Secondly, we'll focus on review the practical applicability from different aspects, considering the different ammonia level, the long-term operation, and the solar applicability, as well as the most innovative part, the mechanism investigation. This is the world first study that revealed why the light can affect the anaerobic community and the AD system. So let's get closer and start from the background part. The anaerobic digestion is the green technology to convert waste into renewable resource. Though it holds a great potential, it still meets some challenges. And during this process, the protein degradation could generate a large amount of methane, a large amount of ammonia, and the high level of ammonia often cause the inhibitory effect to the fermentation microbes or even lead to the failed digester. The inhibitory mechanism shows at here. The generated ammonia ion and the free ammonia are the two principal forms of ammonia nitrogen, and both of them can directly or indirectly cause the inhibition. The ammonia ion directly attacked the membrane enzyme and disturbed the biochemical reaction for biogas generation, while the free ammonia passively diffused across the cell membrane and captured the intracellular protons, and this influenced the proton balance in the cell. In this case, cell forced to pump up more ions to maintain the intracellular pH balance, and this process usually relies on the energy-dependent antiporter, resulting in a higher energy cost in the form of ATP. At the same time, since more ions such as potassium and sodium has been pumped out, this caused the deficiency of intracellular micronutrients, and this interferes the microbial activity, cell growth, and their proliferation. Moreover, the high ammonia pressure will also cause the loss of biodiversity and the metabolic shift into an undesirable direction. So it is necessary to find an effective and reliable strategy to solve this kind of problem. Since the discovery of the anaerobic digestion process, it generally happened in a continuous dark condition without any requirements on the light energy. Therefore, the conventional strategy for mitigating ammonia inhibition are all operated under the dark condition. Though several methods have been proposed, such as the physical, chemical, and the biological method has been proposed for mitigating ammonia inhibition, and the drawbacks such as the complex equipment, secondary pollution, and the long-term operation requirements always limited the sustainable operation and their practical use. On the other hand, our previous study found that by simply exposure to light, the microbial activity was significantly improved compared to the dark fermentation, contribute to the enhanced methane productivity. Since the light stimulation is an easy operated and low cost compared to the conventional process, how about we using the solar light as a light source, which is a clean energy and available all around the world? So with the solar assistance, the newly proposed AD system might be much more efficient and eco-friendly to realize the green innovation of waste into energy conversion. As light can play a vital role in this process, where the light stimulation efficiency largely depending on the critical light parameters such as light intensity, illumination time, and wavelength. So considering the proper utilization of solar light, quantifying the optimal light condition is necessary. So how can we optimize the process comprehensively considering the multiple light parameters? The conventional experimental design for such purpose, for example, the single factor test, is not sufficient in this study, since it's only focused on the individual factors and thus miss the best combination of multi-factors. On the other hand, the RSM was applied in this study. It is a statistical and mathematical techniques for designing, modeling, analyzing, and optimizing a process. By using this method, the relationship between the lighting parameter could be reviewed and their best combination could. So the first objective of my research is to optimize a novel light-assisted bioprocess for promoting the methane conversion under ammonia stressful condition. And moreover, considering the scale-up effect of the proposed process, verifying its practical applicability is necessary. In case of the real treatment process, various operation parameters should be considered, including the ammonia level, the applicability of solar as a light source, or the long-term operation. And then on the other hand, revealing the mystery of lights on the enhanced performance are equally necessary. Generally, the anaerobic digestion is composed of the complex biochemical reaction from the organic to the small molecular fatty acid and to further convert it into methane. And each step requires the cooperation of functional bacteria and archaea, or let's see the methogens we've mentioned before. And specific to the methogens, the methane was produced via various enzymatic reaction. So what is the effect of light stimulation, particularly the solar illumination, on microbial community, the involved metabolic pathway, and the enzyme reaction? On the other hand, the sludge property is another critical characteristic of the anaerobic digestion process, which played a vital role in reflecting the treatment efficiency and the microbial cooperation. So, arriving the light effect from those aspects might help us to better understand the light stimulation strategy and gain the practical use. The second objective is to review the practical effectiveness and the behind mechanism of the developed reactor. Thirdly, as mentioned before, except the intensity and the illumination time, light wavelengths also affected the process efficiency. Especially when we consider the broad solar spectrum, the short or longer wavelengths might induce a varied microbial response in the digester. For example, as you can see, the short wavelengths inhibit cell activity, while the longer wavelengths shows a positive effect on the microbes. And those of the study either operated using the pure culture or energy-dependent light source, which were not economically applicable for future use. While in our research, the mixed culture from waste sludge and natural sunlight as a light source will make the proposed strategy much more visible. And so what is the sunlight spectrum effect on the AD system, especially on the microbial structure and the involved metabolic pathway? So the final objective is to focus on guiding the solar utilization, investigate the effect of different wavelengths, and on the digestion performance. So here we come to the results. Firstly, the optimization of light condition was realized by the response surface methodology, a multi-factor optimization method. A model was established to review the relationship between the two light parameters performance as a response shown as methane yield. And according to the model simulation and prediction, the proposed optimal light condition shows that here contribute to the double methane yield compared to the conventional dark AD process under the ammonia inhibitory conditions. For more detailed, totally 13 rounds experiment was carried out under different combination of two lighting parameters, and after the fermentation, the obtained methane yield as a response is to reflect the digestion performance. And then the data was analyzed by the software. Based on the statistic analysis, a 3D model was proposed to predict the optimal light condition with the best performance, which showing the doubled methane yield under ammonia inhibition. So by RSM model optimization, a novel light-stimulated reactor was developed with the improved efficiency. But we considered that it really worked for the practical use. So in the following, we further confirmed the practical effectiveness of proposed system from following three aspects. Firstly, the system was operated with different ammonia concentration. Because conventionally, the higher ammonia level, the severe ammonia inhibition happened. And the typical ammonia concentration in the nitrogen-rich waste ranged from 2,000 to 8,000 milligram per liter. As you can see, the higher ammonia level leads to the lower methane yield or even field performance in the dark reactor, while the lighted reactor showed higher adaptability with a robust efficiency of twofold increasement in methane yield across the different ammonia levels. Especially when ammonia concentration reached the 8,000 milligram per liter, extremely high level, the dark reactor was totally filled, while the light system still showed the methane production. This suggested the applicability of the proposed light system for treating most kind of nitrogen-rich waste and handling the ammonia stressful condition. And secondly, we compared the system performance with different light sources, especially with the two simulated solar light, with the UV part and without the UV effect. As you can see, the solar light stimulation without the UV wavelengths showed a similar promoting efficiency with the incandescent light, whereas the UV radiation content led to the similar methane yield with the dark reactor, which might probably due to the possible UV impact on the microbes. So to prove our hypothesis, the microbial activity was analyzed using the two microbial indicators. And ATP is the energy carrier that can reflect the cell activity, and coenzyme F420 is a critical enzyme, particularly for methane generation. As you can see, when cutting the UV part, both of the light groups, although with a different wavelengths, shows the higher microbial activity, while when including the UV part, the repressed performance was observed. So the result indicates that the proposed system was effective in activating microbes under the solar illumination, and cutting the UV part is necessary for the future application. Thirdly, the long-term applicability of the system was revealed under different ammonia levels for 2 months, which showed that the light-activated microbes contribute approximately threefold methane production compared to the reduction in 2 months operation under ammonia stress. This indicates that the proposed system was effective in long-term practice, even with the higher ammonia levels and organic shock. So why this system is robust and efficient? Aspects, including the variation of microbial community, the metabolic pathway, and the sludge properties. Light stimulation increased the bacterial diversity, forming a cluster with the methanocecina, which is a robust methane-producing archaea. And moreover, the critical enzyme in methane conversion were highly activated, contribute to the high methane productivity. And finally, the hydrophilic under light and contribute to the defense strategy and the efficient cooperation between microbes to resist the ammonia toxicity. Therefore, the developed system could maintain a sustainable performance during the long-term operation. So let's take a closer look into the microbial community. We found that under the optimal lighting has induced an efficient syntrophic association between bacteria and methanogens. As shown in this figure, two fermentative bacteria, two estrogens, and two methanogens cluster closely surrounded the optimal lighting mark. And these clustered microbes trigger a syntrophic conversion from glucose decomposition via the organic acid oxidation into acetate and hydrogen, and finally generated methane through the different methanogenic pathways. And the when we observed from the biocluster, it gives us more information. This slide shows the biofuel morphology from each reactor under the optimal urination, unoptimal urination, and from the conventional dark reactor. And the significant differences between the lighted groups and the dark reactor is that the lighted groups shows the increased microbial density with the multi-species colonies formed, while the fewer aggregates was observed in the dark. Besides, the cell morphology under lighting varied a lot, indicates improved microbial diversity under the light stimulation to resist the ammonia inhibition. Moreover, light assisted to form a multi-layered colonies which hardly observed in the dark condition. As you can see in the zoom-out figures, the rod-shaped bacteria, which marked in blue, tightly twisted with the Mastnosacina-like cells that highlight in red, achieving a compact methanogenic cluster. But when exposed to the intensive light, the cell was shrunk to the smaller size and the membrane surface was uneven. And this change may due to the possible light stress induced by the intensive lighting, which further evidenced the necessity of optimizing the light condition. So, except the story told by the biology, the chemistry also revealing the light influence from a more delicate level. Here shows the activity of critical enzyme during the methane producing pathway, and generally the methane was produced mainly through two pathways, either utilize hydrogen or acetate as the energy source. When utilizing the hydrogen, it first oxidized by the dehydrogenase and generated electrons was transferred by the coenzyme F420 as we mentioned before, which is a unique enzyme in the active methanogens. On the other hand, the uptake of acetate required ATP to support, followed by the redox reaction which facilitated by the NADH. And finally, these two pathways share the same path to generated methane. So as you can see that the activity of all the tested enzymes were effectively improved by the light stimulation, which could be the key reason for improved methane yield. Moreover, it has been reported that at the final step of the methanogenesis, one part of this critical enzyme could be only activated under light. So all the results suggested that light effectively promoted the dual methane producing pathway. And thirdly, as previously described, solar would be the potential light source for the future use, but considering the broad wavelengths of the sunlight spectrum, it is necessary to understand the wavelength effect. So in these publications, the effect of different wavelengths on the anaerobic digestion process was investigated, the conversion pathway, the microbial structure, and energy metabolism was analyzed. We found that each wavelength played a different role in influencing the process and microbial activity, while by combining the beneficial effect of all the wavelengths, the visible light stimulation performed the best in activating microbes. This novel insight provides a foundation for guiding the future solar utilization in practice. So as a summary, in my research, for the first time, a light-assisted bioreactor was optimized by response surface methodology for thriving ammonia-stressed anaerobic digestion and for guiding the future solar-assisted process. And based on the robust efficiency under different operation conditions, the proposed process shows the high potential for the practical application. Moreover, the revealed mystery of light could provide a basic information on guiding the practical application. In future, this lighted bioprocess with the solar system would be economic feasible for waste management and energy conversion. So for future plan, we aim to further refine the light-assisted system, integrating it with solar power at a large scale to make it a fully renewable, low-cost solutions for treating organic waste. Additionally, we plan to test its adaptability in handling various types of waste, including the wastewater contaminated with the antibiotics, microplastics, and other pollutants. And it's expected that the developed system could contribute to the converting the bio-waste into the bioenergy, for fulfilling the energy demand, creating a new solution for sustainable development. So after the exciting science, now let's talk about your future in the sciences. And a degree in biosciences opens up many incredible career paths. So let's start with the career choice as a researchers. This is for those of you who are deeply curious about the scientific phenomena and are never satisfied with just the textbook answer and want to dig out the behind mystery about how and why. We will some we will see some examples as researchers. For example, as a synthetic biologist, what you actually can do is to design the genetic program to make microbes produce everything, either from the biofuels to life-saving medicines. You can be a programmers, not just for apps, but also for life itself. On the other hand, the environmental bioinformatics use the power of AI and big data to solve microbiology mysteries or track the trends of pollution. Actually, India has a hub for this research, and especially in the areas such as algae biotechnology for carbon capture, as the CSRI, the Council of Scientific and Industrial Research, or the bioprocessing as the renowned ICGEB, the International Center for the Genetic Engineering and Biotechnology. To be honest, this path is challenging and it often requires a PhD and your full energy. But the exciting point is that you can create something new that didn't exist before. You can push the boundary of the scientific knowledge and addressing the unique environmental challenges. Next is the bioprocess engineer, which is the scale-up professionals. What you actually can do is to turn the lab breakthroughs of the new discoveries you found in the lab into the mass production at a large scale. For example, designing or optimizing giant fermenters for things like biojet fuel from the algae. This is a core strength at place in the IIT, the India Institute of Technology, or ICT, the Institute of Chemical Technology. Or if you love plant, you can become a cytoremediation scientist. For example, this is related to the developing specific plant that clean up the heavy metals or toxins from the contaminated soil or water. And as I found on the internet, at the NBRI, the National Botanical Research Institute, researchers are tackling real problems like developing the genetically modified plants to absorb the toxic from the groundwater. So for these two paths, one scale up the solution, another uses natural owned tools. Both of them are crucial for sustainable future. Or maybe you love science, but you want to see its impact on the market and the society. That's where the green industry and the cross-disciplinary career come in. Firstly, you can think about being a specialist in energy and circular economy. Companies focus on the green innovations needs specialists who can take biomass and convert it into the value-added byproducts such as the biofuel, ethanol, and clean hydrogen. This requires combining your skills in process engineering and life cycle assessment to build a truly sustainable system. And secondly, there is the field called carbon and the ESG, the environment, social, governance. Especially complying with the Indian new carbon credit trading scheme, a new job category called carbon analyst was explored. As a carbon analyst, you will measure the carbon footprints, manage a system of carbon credits, and ensure the compliance. Integrate perfect combination of data analysis, policy understanding, and the environmental sciences. And thirdly, of course, as an industrial scientist for the research and development, you can either develop the new enzyme for detergent and create a new biopesticide for agriculture, or the healthier probiotics for those companies. You can do cutting-edge research in microbiology, fermentation technology, and analytical chemistry to create sustainable products. But if you are a great communicator who also understands the science, so I suggest you become a policymaker. You can work for the Ministry of Environment or a non-government organization, help them to create a smart regulation based on the science you have learned. For example, you can translate the scientific concept into the sensible regulations for the genetically modified products. You will become the essential link between the science and policy. Or you are the problem solver with a strong willing to build something new. Then please think about setting up your own biotechnology business and create job. For example, you can found a startup that makes leather from mushroom or plastic-like packaging from seaweed. And finally, if you love both science and storytelling, then become science communicator or journalist can also be your choice. You will work with platform and social media, investigate and explain the latest climate changes and biotechnology innovation to the public. And that career path is an essential translator between the lab and the society. Above all, if you want to be one of them in the future smoothly and successfully, please start building your own toolkit right now. Here are some suggestions from my experience. So firstly, master the fundamentals in your school lab. Please pay close attention during the classes, either in the chemistry when you learn the titration or in biology when you practice the microscopy. And these hands-on skills are your precious foundations for pursuing the future academic degree or position in a company. Secondly, this is also critical for young generation. Please become the friends with the data. You can start by using the Excel to analyze the simple data set from the biology experiment in your school, and then to explore the online resource to learn the basics of our language. Because from my experience in modern biosciences, master the data analysis is not just an option, it's your superpower. And finally, please test your skills in the real world. Please take every chance to participate in the competition, either it's national or international. There's no better way to say if you love the process of science than by doing a project from the start to finish. It also looks amazing on your university applications and teaches you how to think as a scientist. So at the end, please remember this. Previous generation identified these environmental problems, but your generation are the first who have scientific knowledge and the technology tools to actually solve them at the fundamental level. The biotechnology are becoming the most powerful tools we have to heal our planet. And the career paths we discussed are not just the job, they are callings. They are chance to build a healthier, more sustainable world for everyone across the globe. So you will be the scientists, the engineers, the founders, and the policymakers who write the next chapter. You are not just the future. I believe you are the one who will illuminate the future. So finally, thank you for all your brilliant attention today. It has been a great honor to share this with all of you. Today, I also have bring some very exciting news from Japan for you guys. We are launching a brand new international undergraduate program at Kyoto University of Advanced Science and the Bioenvironmental Sciences International Program right from this year in the next month. So this program is designed for the next generation of green innovators, for students like you who see the biggest challenges require the interdisciplinary solutions. This is for those who want to master the power of biology and chemistry to build a truly sustainable future. So, if today's topic I give to you has excited you, I strongly encourage you to come and join us, and perhaps one day you will be the one on this stage, sharing your own incredible discoveries. So, thank you for once again for your wonderful attention and participation. Now, welcome your question and comments. Thank you.
Thank you, Dr. Zhu, for introducing us to such awesome ideas and also the unique programs, the unique pathways that you have introduced to all the students here. Yes, we are open to all the question and answers. Please, could you put your questions in the question box or in the chat box, please? Anyone has any questions? So we have a message from Sanya. Absolutely delighted to view the whole research project for you, Dr. Zhu.
Oh, I see. Let me check the box. Oh, thank you. Thank you so much.
Okay, any questions that anyone has, please? We're here to solve all your queries. Okay, I guess Dr. Zhu has explained everything very well, that nobody has any kind of questions. Okay, yes, Sanya, you have raised your hand. Could you kindly put your question in the Q&A box or here in the chat? Sanya, would you like to tell us your query? You've raised your hand.
Hi, everyone. Good
Hello.
evening. So I was just wanting to ask, like, this project is heavily like light dependent. So while the tropical countries would be at a great benefit, with the project, but the countries which don't receive much sunlight, will it be like we create some artificial sort of wavelengths and then proceed with this project in those countries, or is it that it's primarily for tropical countries?
I think thank you for your answering this. Thank you for your question. It's really wonderful question. Actually, we are thinking about for the future plan. So in my image, actually, our laboratory has now also focused on the solar tracking system. So in the future, we consider combining the solar tracking system and concentrated solar energy into the anaerobic digestion. This can fulfill the most places that do not have the less the tropical area.
Great. That's wonderful to hear. Thank you.
Thank you. Thank you so much for the question.
Okay, do we have any more questions? We'll be happy to unmute you. We'll be happy to receive your questions in the chat box or in the Q&A box, whatever is convenient. Okay. Thank you, everyone. I guess we don't have any questions. We would love to have you again here. Thank you, Dr. Zhu, for the presentation and your thoughtful insights about the program. And Mr. Kandarp and Mr. Takeda-san for joining us. And of course, all the students, counselors who are here for the session. Thank you for taking the time out. We would love for you to fill a feedback form, a very short 5-minute feedback form if you could fill. I'm just putting the link here in the chat box for everyone. If you guys could fill the feedback form to give us some kind of feedback for our next sessions, that would be very helpful. Okay, we have a question from Aratrika before we all leave. What skills should students in fields outside science like art, psychology, or design focus on if they want to help climate solutions?
What skill should students in field outside science they want to help climate change? Probably I have shown some specific skill that you need to set up before join the courses. And for the students who are not, really familiar with the sciences, such as your focus on art, psychologist, or design, I think at least, as I mentioned, that you can learn how to treat with data because our world, our society is composed of data, and now it's data control all of the things to management to the operation of society. So the skills of how to analyze the data, how to collect data, how to summarize data into a visible and vivid result is necessary to all of the students or scientists. And I believe if you can control it, if you can master it, it's play a good foundation for all the paths, all the career you choose in the future. Yes.
Okay.
I think Devakshit, the form is not accessible, requested access. Can you please give that?
I will share it. So I think you'll have to be, you'll have to have a Google email ID for that. So in case you have a Google ID, I think then you'll be able to access the form. Okay, yes. So now I've put this form on a setting. So sorry for that. If everyone can just go back to the form and fill the Google form for the feedback, it would be great. You'll be able to access it. And yes, thank you so much. If we have any other questions, you can still put them in the chat box. And please, thank you so much everyone for joining. We'll wait for 2 more minutes for any more questions. And it would be great if you could fill the feedback form for us in the next 5 minutes so that we can get the feedback for any next sessions. Okay, great. I guess we don't have any more questions. Thank you so much, everyone, for joining in. Thank you, all students and counselors, for being here. It was great hosting you all. I will see you in the next session for our road less taken. Thank you so much. Thank you, everyone. Thank you, Dr. Zhu. Thank you, Takeda-san.
Thank you.
Thank you, Kandar.
Thank
Bye,
you, Devakshit.
everyone.
Bye.
Bye.